this may not be an obvious concept, but whenever we make a measurement, first of all, we have to have units associated with that measurement, but what may not be obvious is that there is uncertainty associated with that measurement. And the idea is that if I step on a bathroom scale and it says that I weigh 166 pounds, I don't weigh necessarily exactly 166 pounds. I might weigh 166.1, 166.2, 165.7, and the scale is still going to report 166 pounds. So in other words, there's uncertainty in that measurement, and the uncertainty is actually in the last digit. So in other words, 166 really means only that we can say that I'm more than 165 and less than 167. So conventionally what people say is that if they write 166, what's implied is that it's plus or minus 1 in the last digit. In other words, if it's minus 1, 165, and if it's plus 1, 167. And we call this the uncertainty, and the uncertainty appears in the last digit. I mean, we know that it's not 170, right? That would be uncertainty in this digit. We know it's not as high as 170, but we can't be sure that it isn't as small as maybe, a hair above 165 or just a little bit below 167. Now, that notion of uncertainty is important when we're making measurements in chemistry or in science in general, because what we report is we report a number and it has an implied uncertainty associated with it. So I can pose the question, is there a difference between 166 pounds and 166.0 pounds? And to you as a person just stepping on the scale, maybe not. But to a scientist, there is definitely a difference, because 166 implied uncertainty of plus or minus 1 means that the value that we measured can be between 165 and 167. We know it's bracketed by those two numbers, but we can't be precisely sure about what the real value of the number is. Whereas 166.0 has a different implied precision. The precision is in the last digit, and the last digit can vary by plus or minus 1. Plus or minus 1 in this digit. So in other words, the number is between 165.9, which is this number minus 0.1, or this number plus 1. So in other words, we've narrowed the region or the range over which the measurements are going to appear. So if we repeat the measurement more than once, on the bathroom scale, we'll always get numbers between 165 and 167, whereas if we have this super colossal, really expensive bathroom scale that measures to tenths of a pound instead of just to the nearest pound, then our measurements are going to appear in a narrower range. And what we say is that reporting it as 166.0 is more precise than reporting it just as 166. One thing I forgot to mention is that the symbol for pounds is lb, so you're going to see lbs after all my measurements. Remember, measurements always have units associated with them, but if this looks like 16, I apologize for my handwriting. Remember, it's lb for pounds. I have no idea why lb is the unit for pounds. Now, precision is tied to the concept of random error. And unfortunately, random error is a poor choice, but that's just what it's called. It isn't random in the sense of rolling dice. What it's random in is that in the last digit, you have to sometimes, in fact, you always have to guesstimate. Guess, estimate. And those two, that idea is what is known as random error. So when we say that something has high precision, what we mean is that we can make the measurement over and over again, and the values fall within a narrow range, taking into account the fact that you have to guesstimate the last digit. And let's see what I mean by that. So precision, again, reflects the uncertainty in the last digit. If we can know that last digit, then we can say that the number is more precise. And rather than belabor that point, let me just show you my illustration. Suppose we want to measure this pink bar here, and I have a blow-up of a ruler, and this ruler happens to be measured, marked in centimeters. Then if we have to know, using this ruler, how long this pink bar is, the best we can do is, well, we know it's between 1 and 0. And furthermore, we can actually guesstimate what the next digit is, because we can say qualitatively, okay, well, it's a little bit longer than a half, and it looks like it's less than 3/4, right? Here's 3/4, here's a half. Let's say that it's about 0.7. So in other words, beyond whatever is marked on the ruler or on the bathroom scale or whatever, you can always guesstimate the next digit, and the next digit in this case is going to be, say, a 7. So we know it's between 0 and 1, but we can do better than that. We can say that our pink bar is 0.7 centimeters. And that involves that guesstimate that I'm talking about. And you always have to do that with the measurement because the device that you use, there's always some intrinsic limit. In other words, in this case, the bar is marked down to centimeters, and so you can go one better than that and guess the next number, which is the 7, but there's uncertainty. It's, between 6 and 8, but we don't know for sure that it's exactly 0.7. Now, if we had a different ruler, one that was, say, marked in millimeters as well, now we can actually improve our precision because we can say for sure that not only is it between 0 and 1, but in fact it's between 0.6 and 0.7. And then once again, we can guess what that next digit should be. And so using our ruler that has more demarcations, we can say that the number is now 0.6, and we can guess the next digit to be 5. Okay? What does this say? 0.7 says that the number is 0.7 plus or minus 0.1, meaning that the number is really between 0.6 and 0.8. And now with our better ruler, we can say that this is 0.65 plus or minus 0.01. So we've made a more precise measurement with this ruler than with this ruler. Okay, now the other term that you have to think about when you're worrying about measurements is accuracy. And accuracy is how close your measured value is to the hypothetical true value. So I weigh something, and I don't know exactly what I weigh. The scale tells me that I weigh 166. And somewhere, in a theoretical sense, there is exactly what I really weigh, and the scale just measures and tells me approximately what I weigh. Well, accuracy then is how close you are to the real true value, and it depends on the quality of the instrument that I'm using. For instance, is it calibrated? So understand that accuracy is not about how many marks does it have. It actually is a reflection of how good is my instrument. For instance, imagine I'm stepping on this bathroom scale, and the bathroom scale tells me that I weigh 166. And suppose I didn't notice that, in fact, before I stepped on the scale, it was actually set up on -1. So in other words, it wasn't exactly 0 when I got started. Well, that's going to give me the wrong answer. It's going to give me the wrong answer because the scale that I'm using isn't accurate. And in fact, it's entirely possible for a measurement to be precise and not even accurate at all. For instance, I could have the scale that tells me that I'm 166.0 pounds, and if I measure it again and again and again and measure myself over and over, I'll keep getting 166.0 pounds. But if the scale wasn't calibrated, in other words, if it started out at -1, I might really weigh, my true weight is going to be 167. So I'm getting a reproducible number that I can express to a very precise value, but it's just wrong. And that's an entirely possible situation, that if you have a device that just it gives the same answer over and over again, but the answer isn't tied to the true answer, then it is precise without being accurate. And I'll give you an example of that in a second. Now, accuracy, in contrast, is tied to the idea of a systematic error. If you have a systematic error, what it means is that your system is no good, that your system, being the scale or the ruler or whatever, isn't any good. It could give answers in a very narrow range, so it could be very precise, but if it's wrong, if it's just not close to what the true value is, then we'd say that it isn't accurate. And a great example of that is a clock that maybe measures in milliseconds. A millisecond is a thousandth of a second. And maybe it gives us a very precise number about what time it is, but suppose it's 5 minutes fast. Well, it's 5 minutes fast, meaning that it's giving the wrong time all the time, but it's giving it down to the millisecond. Now, that could be useful still if you know what the error is, if you know what the nature of the error is. For instance, if your watch is always 5 minutes fast, you know what time it is. But in general, what we're going to see is that numbers that are precise tend to be more accurate. So in other words, if you can express things down to milliseconds, if a scientist can come up with a device that measures down to milliseconds, usually it's also going to be accurate, meaning that it's also going to be close to what the true value is. And the flip side, so you might have said, okay, well, we can have a number that is precise but not accurate. Can we have something that's accurate but not precise? And that's sort of a bad term. In other words, it's not really meaningful to say that something is accurate but not precise, because remember, accuracy refers to how close something is to the true value. And so if the data are scattered, so in other words, if the values appear all over the place but they just average out to be close to what the true value is, that's not really meaningful. And the best way to understand this concept is to look at someone playing darts. So what we're going to do is we're going to go to the pub and we're going to throw some darts, and I'm going to finish this lecture there. But the bottom line is that for something to be accurate but not precise is not really meaningful, whereas precise but not accurate is very meaningful. And generally, the more precise something is, the more accurate we at least hope it's going to be. We're here at a local Austin watering hole to finish our discussion of precision and accuracy. And the classic analogy for precision and accuracy is a game of darts, where the true value is given by the target and the precision indicated by how close the darts are clustered together. So what we have here certainly is a throw that is precise, and this is the first throw that I made today. So even before the cameras were set up, I just walked up. I haven't played darts in a couple years probably, grabbed the darts, towed the line, and threw these 3 darts, I swear. And you can see that that we have a precise measurement. The darts are close together. It might seem to you that it isn't a very accurate throw if you thought that the target was the bullseye. But in fact, as any true dart player knows, you shoot for the triple 20, and that's what my target was. So that's what we're going to call the true value. And you can see that my measurement was very close to the true value. So this is both a precise and an accurate measurement. Now let me show you what the analogy would be for a measurement that is neither precise nor accurate. Now, the way Professor Harmon throws darts is like this. And that throw is certainly not precise because the darts are not clustered together, but it also isn't accurate in the sense that if the target were the bullseye, the true value lies, somewhere close. But you can see that the concept of accuracy also requires precision. In other words, you can't be accidentally accurate. You're certainly not going to win any tournaments with throws like this, even if the average value is somewhere close to your target. And finally, let me show you what a throw that is precise but not accurate. That would be a throw where the darts are clustered together but nowhere near the true value or the target that I'm aiming for. So let's suppose that the true value is still the triple 20, and then now I'm going to throw the darts, and let's see how well I do for aiming for a precise measurement. Okay, this is obviously not as good as what I did before, but you can see that the darts are reasonably clustered together. So that would suggest that they are reasonably precise. Not going to win any tournaments with this either, but not accurate, meaning not anywhere near the triple 20. And finally, let me try again to see if I can throw at the triple 20 something that is both precise and accurate. 2 out of 3 isn't bad. It's not good either. But again, let me remind you that precision is reproducibility. It's how close the individual measurements cluster together with each other. And so this is not real precise. If it were like that, that would be precise. And then accuracy refers to how close our measured value is to the true value. In this case, the true value is the triple 20, so we're not super close, but it's not bad either. And that you can have a measurement that is precise but not accurate, such as a throw where the darts are clustered together but nowhere near the true value. And a throw that is accurate and precise is one where they're clustered about the true value.